Okay, so hello guys. Welcome to another problem solving session with Special Maths Academy. My name is Obukume Jaife, and today we're looking at problem one of the recently conducted PAMO that was held in Rwanda. On between 14th to 22nd of May. The first problem there is a geometry problem. It says in a triangle ABC with AB less than AC, D is a point on segment AC such that BD equals CD. A line parallel to BD meet segment BC at E and line AB at F. So they said point G is the intersection of AE and BD. So we have to show that angle BCG is equals to angle BCF. Okay, so that's the problem. So let's take that. And so ideally in a geometry problem, the first way to start would be to draw a diagram. So let's just draw like a diagram first. So we have let's not draw something too big. So they said AB is less than AC. So assuming A is at the top. So assuming this is A, then AB has to be less than AC, so it means AC has to be longer. So we could have something like this. So this kind of diagram kind of like is kind of like showing that not the best representation, but it works fine. Okay, yeah, so we have here C. So this AB less than AC means that this angle B, it just means that angle B is greater than angle C. That's what it means. It just means angle B is greater than angle C. So supposing we called angle C theta, we can like call here theta plus something. Let's say theta plus alpha. So they said there's a point D on segment AC that's between D, A, and C, and such that BD equals CD. That these two places are equal. That means this is theta. Okay, so it means this smaller part here is theta, and the other part outside is alpha. Okay, sorry about that. Yeah, so you can see why the greater than condition is possible, so we can have this division. So we have that. Then they said a line parallel to BD, okay, so mid segment BC at E and line AB at F. So since they said line AB means the extension of AB, so there's a random parallel line, something like this. So these two lines are like parallel, right? Okay, so we have these two lines being parallel, and instead it meets BC at E and it meets AB at F, right? So then I said the point G is the intersection of AE and BD. So we have yeah, okay, let's use red for that point. Okay, let's use green as point G, this intersection points of AE and BD. So they said we should show that angle BCG, okay, if I join here to here. So they said I should show that our job is to show that BCG, okay, so show that BCG, okay, something like this. This BCG is equals to BCF. Yeah. So show that this. So let me mark it. Yeah. So let's make here blue. So show that this, and let's mark this other part BCG as red. So let's show that BCG equals BCF. This is what I should show, BCG equals BCF, right? So this is what we want to show. So a good way to start would be if you look at this diagram, there are a ton of cVans, like cVans, like lines from vertices of the triangle just going around. So a good way to start would be to think about that. So let's try chasing angles first. Let's see what we have. So you can say let angle BCG be x, yet here be x, and let the other part be y, the one we're looking for. That's here. And let's okay, let BC, okay, rather let BCF be x, and let this be f. Let BCF be x, and let BCG be y. So we want to prove that x is equals to y. This is what we want to show. So we can first start by using some angle chasing. We don't really know what's going on. So if this is alpha, we know that this is also alpha from like corresponding angles, parallel line stuff. So let's think about this now. So I can see that in triangle ABC, I can see that BD and then AE and CG, they concur, right? They are concurrent lines, like they concur at G. Then on this side, I can also see that in the bigger triangle, in triangle A is AFC, this is F. We can also see that we have the same AE, we have BE, and you have CB concur at E. So one thing I would want to say, it's the motivation. So with this concurrent stuffs everywhere, and there are really limited freedoms in terms of what you can do with angles. Okay, we could also say yes theta, but it doesn't really give us much info. So one thing I would say is a good way to think about this would be to think about this using trick-saver, the trigonometric form of Sever's theorem. Like that would be a good way to start. And I think that works fine because we have like some angles in between, and I feel things will like cancel out. So let's start with that. So I'll clean this out now. I want to use the trig form of Sever's theorem now. I think that would be a good way to start because of the concurrency points everywhere. Okay. So from triangle ABC, using trig saver, we know that the sine of angle, we know the sine of this over this, that is sine of angle BAA over sine of angle EAC. That's like, you know, the normal, if we're using normal saver, it's something like normal saver, the like standard version or standard, it will be something like BE over CE times, that is this over this, times CD over AD. Then if I extended this G to some point here, so maybe say H times AH over BH equals 1. This is the normal saver, but the trig form now is not taking the angle. So BE over CE, I will not take the angle opposite BE, which in this case is angle BAE, and the angle opposite CE, which is angle EAC now. So I'll not replace this ratio. So in place of BE over CE, I'll now put sine of angle BAE over sine of angle EAC. So that's how the trig form of the saver works. It's just like the normal one, that we're now using angles now and sines instead of just ratios of sides. So we have the sine of angle BAE over sine of angle EAC times sine of angle CBD over sine of angle DBA, which is signifying CD over AD, then times sine of angle ACG, which is signifying AH over BH over sine of angle BCG is equals to 1. So we cannot plug in what we know. We don't know what BAE and EAC are, so we can still keep this. Then we know that CBD is theta and DBA is alpha, so we can say sine theta sine alpha Okay, we call this place y. Okay, we call BCG, which is BCG, which is what we're looking for. We'll call it y. So this will be sine y. Then you know ACG is this entire angle here. ACG will now be theta minus y, right? Because this is y and the other part, the entire angle here is theta. So this will be theta minus y. So you can see that ACG is angle ACB minus angle BCG, which is theta minus y. So you see why that has to be theta minus y. This is sine theta minus y equals 1. So let's just keep this identity first. It can come in handy soon. So you now come to the bigger triangle, triangle AFC. This is point C, so we don't forget. So from triangle AFC, from triangle AFC, we know that in this case, sine of angle FAE, which is, okay, let's extend this down now so you can see. Let's call this point a random point. Let's call this point K. Then you know that FQ over KC will be sine of angle FAK. Okay, let's use FAK over sine of angle KAC is equal times, this is for this over this, then we now have times sine of angle CFE, which is now this angle here now. So we're concerned with this one now. So you know this is but we can actually get this because you know this is theta, and we know this is also theta. We know that angle, now let's do some angle chasing again. We know that angle BEF is equals to theta, alternate angles, right? We know this is true. Angle BEF is equals to theta because angle DBC is theta, and these two lines are like parallel. So these two are parallel, so this means this is also theta. Then we know that this plus this has to be equals to theta. This is theta minus x. This is theta minus x from the exterior angles theorem. We know that our angle EFC is theta minus x, reason exterior angle theorem. Exterior angle theorem. So we can like keep with this. So this is theta minus x. So in place of this, so in place of sine of angle CFE, we can put sine theta minus x over sine alpha. Then times the last one, which is sine okay, that is sine theta over sine x. So in case you don't know which cvariance you are considering, this is also equals to 1. So we're using the fact that AK from, this is from the fact that AK, FE, and CB are concurrent at E in triangle AFC. So let's call this identity. Let's call this first one we derived from ABC1. Let's call this 2. Then both of them are equals to 1, right? So that means both of those identities are like equal, right? So since they are both equal to the same number 1, so it means that sine of angle BAE, now note that 1 and 2 are equal. They are equal. So this means that sine of angle BAE over sine of angle EAC times sine theta over sine alpha times sine theta minus y over sine y is equals to sine of angle FAK over sine of angle KAC times sine theta minus x over sine alpha times sine theta over sine x. These two are both equal, right? So we can see on this side, you can see sine theta will go out, sine alpha will go out. Then for these two, if you look from the top, you can now come to your diagram and see that BAE, then you can see that if you come this way, now let me clean this. We don't need all this part anymore. So we can like have some space. Let me clean this so I can like illustrate what I want to show. So if you notice, you can see that angle BAE is equals to angle FAK, right? Can you see? This is BAE, this is FAK. So they are basically the same thing. Similarly, you can see that angle EAC is equals to angle KAC. So you cannot use that knowledge. Okay, so you can come down now. And this means that automatically, since BAE is equals to FAK, means sine of BAE is equals to sine of FAK. So these two can like go out. And since EAC is equals to KAC, means these two can also go out. So on the end, we are left with just sine theta minus y over sine y equals to sine theta minus x over sine x, right? So we can cross multiply now. If you cross multiply, this means that sine x sine theta minus y is equals to sine y sine theta minus x. So at this point, I think your mind should be going back to this sum to product identities. You know that we have that this, cos A minus B. If you remember, this is cos A. I just want to like show you where the identity is coming from. Is plus sine A sine B, right? I know that cos A plus B, this is going to come in handy now. It's same thing as cos A cos B minus sine A sine B. So if I subtract cos A minus B from cos A plus B from cos A minus B, I have something like cos A minus B minus cos A plus B is equals to 2 sine A sine B, right? So dividing both sides by 2, then I have that if I divide both sides by 2, I have that sine A sine B is equals to half into cos A minus B minus cos A plus B, right? So this is like cool because then I can use this. So let me put this in. So if I use this means that if I use that cos identity, it means that sine x sine theta minus y will be equals to, I can call A as x and B as y. It will have cos half into cos x minus theta minus y minus cos into x plus theta minus y, right? Similarly, I can repeat the same thing for sine y sine theta minus x. So I have this as half into cos. So this place A is y now, y minus theta minus x minus cos. Then I sum both of them, y plus theta minus x, right? So these two are equal. They are equal to each other. They are like the same thing. So it means that these are also equal. So this means that I can just like remove the half. So this means that this, the one in blue, is equals to this one. Let's use the one in green, equals to the one in green. So I can just leave out the half, since the halves will cancel out when I equate both. So it just means that I have that cos, if I, this is expanding the bracket now, this is x minus theta plus y minus cos x plus theta minus y is equals to cos. If I expand this is y plus x minus theta minus cos y plus theta minus x, right? So we can automatically see that x plus y minus theta, x plus y minus theta, these two cancels out. So the minus minus from here also goes out. So just remaining cos is equals to cos. So it means to this two being the same thing means, if you can recall, you know that the cosine is an even function, right? So we know that cos A, if you have two angles A and B being equal, then this means that either A is equals to B or B is equals to minus A, because you know that the second case is follows from the fact that cos A equals to cos of minus A. I think this identity is well known. This is well known. I mean, this is cosine being even is an even function, so I can use that. So if I use this, since cos this is equals to this, let's call this star and star star, it means that either x plus theta minus y is equals to y plus theta minus x, or x plus theta minus y is minus y plus theta minus x. So if I use this, you can see the first one that theta cancels out, then I have something like this one will simplify to something like 2x equals to 2y, right? Y comes this way, x comes the other way, and this means that x is equals to y for this first one. Then for the second one, if I use this is x plus theta minus y equals minus y minus theta plus x. So plus x goes out to plus x, minus y goes out minus y, and this implies that theta equals minus theta, and this means theta equals 0, which does not make sense. So it follows that the only case that makes sense for these two cases is x equals to y, but that's exactly what we wanted to prove, because if you remember when we started out, we said we want to prove that x equals to y, and x, now you recall that angle BCF was equals to x, and angle angle BCG was equals to y. Then since x equals to y, since we have gotten this means that angle BCF equals angle BCG, and QED means the proof is complete. So that's how you solve this problem. It was an interesting problem, like just basic trig identities, and once you know several, everything should actually fall apart. So I hope to see you in the next video. My email is on this page. If you have any questions, or if you have any way you don't understand, just feel free to reach out to us. Then stay with Special Maths Academy. Follow us on social media. Our summer camp is coming, and we have something big planned for you guys. So till then, and see you in another problem solving session.